All right, so first of all, we're going to give you a formal definition of a rational function. So a rational function f of x is going to be defined as n of x over d of x, where n of x is a function of some sort, and d of x is also a function, or a polynomial, and they are over each other. We have a numerator over a denominator. And the big thing that we have to be worried about is that for every x, the denominator cannot be equal to 0. So we can never, ever, ever divide by 0 in our number system. One thing to be aware of is that our numerator and denominator can't have common factors, so we have to simplify first. So we take a polynomial, divide it by a polynomial. We have a good old rational function. And we need to simplify first and ensure that the denominator is not equal to 0. So we have to exclude those values of x that are going to make that happen. All right, so, oops, my apologies. Thought I saw the pencil stop. So when we take these polynomials and divide them by polynomials, we end up having some vertical and horizontal asymptotes. Definitely vertical asymptotes, sometimes horizontal asymptotes, sometimes slant asymptotes. We find the vertical asymptotes anytime the denominator is equal to 0. So in this particular example, we look and we see that if we let x be 0, then x squared is 0. That makes the denominator 0. So that's where our vertical asymptote happens to be. But what kind of blew our minds in our exploration was the fact that sometimes we have horizontal asymptotes that the function actually crosses. So when we define a horizontal asymptote, we don't define it as something that can't be crossed, but we define it as an asymptote provided that that function approaches that line as we get to infinity. So as we approach infinity from the right, we're getting closer and closer and closer to this line, y equals 3. As we approach infinity from the left, we're getting to negative infinity, we're getting closer and closer and closer to that line, y equals 3 again. Question? Only the horizontal, never the vertical. Okay, so we'll never cross the vertical asymptote because that's what makes that denominator equal to 0. But it is okay for it to cross or touch it as long as as it's going to positive and negative infinity, it's approaching the line and it won't touch it again. Great question. So far, so good? Now, I think in Algebra 2, we gave you a primitive view of this. I don't think they ever crossed in Algebra 2, did they? Maybe, at least not that you remember. So there may have been some examples and so forth, but for the most part, we just kind of expose you to it and don't necessarily expect you to master it or see every possible case. All right, so here comes our next slide. In this slide, we talk about the rules of asymptotes. Only what you need to write down. So if you already know this from your exploration, then there's no need to write it down. Okay? Or if you want to summarize it. One thing that they're finding in education is we're kind of swaying back to the point where we're teaching handwriting, cursive writing in elementary again. And the reason that we're doing that is because we found that people learn better if they take notes by actually writing things down than if they type them. And so the reason for that is that when we're writing, we have to decide what's important because we can't write as fast as the speaker can speak. So we have to decide what's important and we have to put it in our own words in order to be able to make makes sense, and that helps us make neural connections in our brain. But if we're typing, a lot of us type fast as someone talks. So all we're doing is putting down whatever they're dictating to us, basically, and we're not having to make those judgments and decide what's important. So here, when we're talking about asymptotes, if you want to just write degree is bigger in the bottom, right? That might be the way that you would summarize this first point. If the numerator's degree is less than the degree of the denominator, right? So the degree is bigger in the bottom, or the numerator is smaller on top, right? Degree smaller on top. Then y equals 0 is going to be your horizontal asymptote. So that was our first group when we were doing our exploration from the very beginning. In that, the denominator had the biggest power, the biggest degree, and therefore it was always y equals 0. In our second group of rational functions that we explored, we had the same degree in both the numerator and the denominator. And when that happened, the leading coefficients divided ended up being the line that was set equal to y. So y equals the coefficient of the numerator over the coefficient of the denominator. And then in the third part that we explored, we found out that the degree in the numerator was exactly one more than the degree in the denominator. And then that meant that we had a slant asymptote. And when we had a slant asymptote, we had to divide the numerator by the denominator to figure out what that line was. So the degree is bigger on the bottom, y equals 0. Degrees are the same, coefficients. Degrees bigger on the top by 1, we divide it and get a slant. Make sense? I still see pencils moving, so I'll make sure we're done. All right. Any questions on this one? All right, so here we go. Plan of attack. The first thing we want to do is we want to simplify, if possible. So when we're simplifying, that means that we are factoring and seeing if there are any factors in common in both the numerator and denominator. And if so, we're going to cancel those out. Oh, no. Yep, simplify the polynomial, if that's possible. And then you're going to find your vertical asymptote, or asymptotes, by setting the denominator equal to 0 and seeing what value of x makes that happen. And you want to sketch those with a dashed line or a different color. This is where your colored pencils or your gel pens work out great, because you can have that extra line that you're going to approach but not touch. And then you're going to find and sketch your horizontal or slant asymptotes. And then it's a good idea to find your x and y intercepts if possible. And then you're going to plot at least 2 points per branch. In other words, make an xy chart. And connect the points with a smooth curve. All right, so here's our first example. We are going to graph f of x equals 2x over x squared minus 4. So the first thing we want to do is we want to determine if they have anything in common. So how does that denominator factor? Yeah, x plus 2, x minus 2, because we have a difference of squares there, don't we? So x equals a positive 2 and a negative 2 for our asymptotes. Does anything cancel? No, we don't have exactly the same thing in the numerator and denominator, so nothing cancels here. So we've already decided what our vertical asymptotes are. We're going to quickly sketch them by drawing a dashed line along those two lines. And then we're going to ask ourselves, are we going to have a horizontal or a slant asymptote, and what would that be? Well, I've given it away. There's a horizontal asymptote here. So the power's bigger on in the denominator, isn't on the bottom. So what does that mean? Horizontal or slant? Horizontal, and what will it be? Y equals 0. So we're going to first write y equals 0 and draw a dashed line along the x-axis. And you can always, from this information, decide what your domain is. The range, we want to graph it first before we decide what the range is, but with the domain, we're never crossing that vertical asymptote, so we can always write down the domain straight from this. So what values can't x be? 2 and negative 2, so how do we write the domain in interval parentheses? Very good. Okay, so everything but 2 and negative 2. And so let's wait on the range, make sure that we don't have any asymptotes that get crossed, right, any horizontals. And then we need to come up with a quick little t-chart. So it also suggested that we find our intercepts. So we're going to plug in 0 for x. Make sense? So when we plug in 0 for x, we're going to have two times 0, 0 squared minus 4. 2 times 0 is 0 over negative 4. We're going to get, we can take 0 divided by something, right? But we can't go the other way, so we end up with 0. Okay, 0, 0 is one of our points. Turns out that's our x and our y intercept, isn't it? Okay. If we were trying to find the y-intercept and it didn't happen to be the origin, we would just say, hey, if I let y be equal to 0, what will x be? When we cross multiply here, what happens? 0 equals 2x, so x has to be, yeah. So it happened to be the origin, so really we took care of them both by just plugging 0 in for x. So far so good? Okay. So we know we have that point, and now we have to plug in something else. What's another number to try? 2? Can't do 2 because let's do 3. All right. So when we plug in 3 for x, we'll have 2 times 3 over 3 squared minus 4. So 6 over 9 minus 4 is 5. We'll get 1.2. So when we plugged in 3, we are 1.2 up. Okay. They won't all come out to nice numbers. Sometimes we get decimals, and that's okay. All right, what's another number we should try? 1. Anybody okay with doing 4 first, so we're working on this branch before we go anywhere else? So let's put a 4 in there. So 2 times 4 over 4 squared minus 4 is going to be 8 over 16 minus 4 is 12, so 3/4. So when we're 4 over, we're 3/4 of the way up. Yeah, we can draw that branch. So we're going to just make a nice smooth curve heading toward the horizontal asymptote, toward the vertical asymptote, and we've got one branch done. Yes, sir. We get for it is, I'm sorry, 2/3. Thank you. Good catch. 2/3 is right. My fault. My apologies there. But as far as 2/3 and 3/4, I'm pretty close to the way, so plotting it didn't hurt anything, but thank you for catching that. All right, next one. What else are we going to plug in? 1. 1's a good one because 1 is allowed. It's not part of our, it's part of our domain. It's not a portion of what we can't do. So when we plug in 1, we're going to have 2 times 1 over 1 squared minus 4. So 2 over negative 3, 1 over, we're negative 2/3 down. Let's try negative 1. When we put negative 1 in, we'll have 2 times negative 1 over negative 1 squared minus 4. So negative 2 over negative 3. And negative over negative is positive. So we'll be 2/3 up. And let's see this. Yeah, kind of like a cubic, right? Only reflected across the y-axis. Okay. Now we got to do a couple more points. So what's another one to try? Negative 3. So when we plug in negative 3, we'll get a negative 3, 2 times a negative 3, and then a negative 3 squared minus 4. So negative 1.5, 1.2, sorry, 1 1/5. So we're at negative 3 and negative 1 1/5. I have a pretty good idea what's going to happen over here. We're going to approach this asymptote. And also, we could do negative 4, right? But let's save some time and know that it's going to do this as well. Now that it's graphed, now we ask ourselves, what's the range? Okay? Why is it all real numbers? Yep, we did cross that horizontal asymptote this time, didn't we? So we don't say everything but 0. Sorry, we're at 2. We know roughly what it's going to look like. On our directions, we said let's go 2 points on either branch, on every branch, but this is going to be a mirror image. We've seen enough of them by exploring that we know that it's not just going to jump over and do something crazy. Yeah, it's fine. Make sense? Question? I would love to see interval notation because that's kind of our grown-up pre-calculus way of doing things. But I understand that all real numbers is really even faster to write than there's a benefit to, a cost benefit to each one. But yes, they're the same, they're equivalent. Okay, so far so good? Any others that you have questions, or any other questions that you have about this one? Okay, let's look at the next one. So new function, f of x is x squared plus x minus 2 over x squared minus x minus 6. All right, so what was our first step that we're supposed to do? Simplify. So we better do some factoring to make sure that we don't have anything in common with both. What does the numerator factor into? Yep, x and x. Factors of 2 that subtract to become a positive 1. Yep, 2 and negative 1. All right, second one. Factors of 6 that subtract to become a negative 1. All right. Do we have anything in common in both the numerator and denominator? Yes. When it's factors, we can cancel. When it's sums and differences, we can't cancel. But when it's factors, we can. And so when we do that, we've just created a hole in our graph. So what I want you to do in some way that you won't forget, put a big star beside it and say that there is a hole at x equals -2, the thing that we just removed. Okay, it was in common in the numerator and denominator, but there's going to be a hole there, and we have to remember to circle back and talk about it. Make sense? All right, so next we say, what's our vertical asymptote? X equals 3, because that's what would make our new denominator equal to 0, right? Dash line x equals 3. Because our new resulting function is x minus 1 over x minus 3. So we have to ask ourselves what's going to make the denominator 0. Okay? We've eliminated what they had in common. We have to remember that we've got to go back and take care of that. There's going to be a hole there. But this is our new result. So far, so good? Okay, so now we say, okay, they have the same power, same degree. So what does that mean? Divide the leading coefficients. So what are our leading coefficients? So our horizontal asymptote will be y equals. So we put our little dashed guy across the line where y equals 1. No, not because of the horizontal making the numerator 0, but because the understood number in front of each of these guys is 1. And when the powers are the same, we just take the leading coefficients and divide them. Well, we'd have a 3 in common again, right? So that could be canceled. Always take out what's in common. But if this had been a 3x minus 1 over an x minus 3, then yes, 3 over 1 would be our y equals 3. It would be our horizontal asymptote. 1 over 1 is 1, right? So far, so good? When you're thinking about the what ifs, that means that you're processing even more, which is good. Okay? All right. Now that we've done this, we can find our domain, because it's never going to cross that vertical asymptote. So what's our domain? Yep, can't be 3, right? So negative infinity to 3 and 3 to infinity, not including them, so we have a parentheses. All right, so we hold off on the range for the moment. Okay, and then we ask ourselves, what are some numbers that we're going to plug in? Well, obviously we want to, if we can, always try 0 for x. That's going to get us our y-intercept. So if we plug in 0 for x, we'll have 0 minus 1 over 0 minus 3. Negative 1 over negative 3 is positive 1/3. So 0 over, we're 1/3 of the way up. Okay. Well, let's try 1. And the reason was there's 2 reasons to try 1, right? When we do y equals 0, what's going to happen here? Cross multiply, this is gone, right? So 0 equals x minus 1. So what's x? Positive 1. So when x is 1, y is 0. So we just found our 2 intercepts. Okay? Can we see what's happening with that branch? Okay? But let's do one more thing, because on that branch is that x equals negative 2. Okay? And that's where our hole is going to be. There's a hole there. Hole in my bucket, dear Liza, dear Liza. Okay? Well, I'll show you. So what happens is we plug in that negative 2 into our new function. And when we put a negative 2 in there, we'll have negative 2 minus 1 over negative 2 minus 3. So we'll get a negative 3 over a negative 5, which is positive 3/5. Okay? But because the original function can't be 2 for x, negative 2 for x, we can't have 3/5 for y either, can we? So if we're at negative 2, we can't be 3/5, can we? So we can't be right here. So we put an open circle there to say my original function cannot allow us to use negative 2 for x. So when we plug negative 2 into this reduced function, we got 3/5 for y. So when I'm negative 2 to the left, I can't be 3/5 up. That's my hole. Make sense? Kind of? Crystal clear? Okay, good. So now this is coming down. We make our nice smooth curve. And we get to almost be negative 2, but not quite. And that's our left branch. Now we're ready for our right branch. So what number shall we try? I like 4. Anything but 3, right? So when we're plugging in 4, we can be 4 minus 1 over 4 minus 3. 4 minus 1 is, and 4 minus 3 is, so 3 over 1 is 3. 4 over, we're 3 up. What else do you want to try? 5. So when we plug in 5, 5 minus 1 over 5 minus 3, 4 over 2. So we're 5 over, we're 2 up. So can we see what that's doing? Make sense? All right, let's see how Desmos does this. Okay, let's do a real quick check. So I went to Desmos and I graphed, whoops, wrong one. I graphed our equation, right? And we can see we have an asymptote at y equals 1 and an asymptote at x equals 3. And watch what happens as I follow this graph. So here I am at negative 0.27, I'm fine. Negative 1.5, I'm fine. Have a y value everywhere, but then what happens when I get to negative 2? I'm going to find out. There's a hole. It's undefined. Okay? Because we can never divide by 0, right? And that's how Desmos will show it. Make sense? Only we don't want to have that be an invisible hole. We want to actually be that hole that we can see all the time. All right, so here we go. Back to range. Negative infinity to not quite 2, to not quite 1. Where's our hole? 3/5. So we can go from negative infinity to 3/5, but we can't be 3/5. Or 0.6 if you prefer decimal. Okay? Then from 3/5 we get to go how high? How high? From 3/5 we get to go to 1. And then from 1 we get to go to infinity. We have to account for that hole that's not defined. Make sense? All right. Questions on this one? Yes. Why is it negative 2? It should be. Thank you for catching that. Okay. So we have a vertical asymptote here. Okay. I did this perfectly the last 2 hours, but I didn't do it here. So negative infinity to negative 2, right? Let's modify that. Negative infinity to negative 2. It can't be negative 2. And then from negative 2 to positive 3. And then from positive 3 to infinity. Thank you for catching that. Okay. Make sense? Okay, so we don't want to completely ignore, just because that asymptote's not there, there is a place that x cannot be, and that is also negative 2. Okay? All right, next one. Slant asymptote. So we said our slant asymptote happens when the degree of the numerator is exactly 1 more than the denominator. So we have a quadratic in the numerator and a linear in the denominator, or a cubic in the numerator and a quadratic in the denominator. As long as the power is exactly one more in the numerator, we get a slant asymptote. To find out what that asymptote is, we just divide, ignoring the remainder, synthetically if possible. But if it's a cubic with a quadratic, we can't synthetically divide. And we find out what that equation is. And here comes our next example, last example. So we want to graph f of x equals x squared minus x over x plus 1. You bet. Okay. So our first step is always to check and see if we can cancel anything. How does the numerator of our function factor? X in common, right? So we take the GCF out, what do we get? All right, since the numerator and denominator do not have exactly the same factors, we can't cancel. Okay. So we say, first of all, what's our vertical asymptote going to be? -1 equals x, right? Always in line, okay? X equals -1. -1 causes that problem of a 0 in the denominator, so x cannot be -1. Our vertical asymptote is x equals -1. All right, so far so good. Whenever we set the denominator equal to 0, we ask ourselves what happened. Yep. What causes that to be 0? So we can work with the domain right now. What's our domain? Yep. That's the only asymptote, the only place we have a problem. So we can be anything but -1. Now, we need to figure out what our slant asymptote is. So slant asymptote means take the numerator and divide it by the denominator, right? So let's do this synthetically, since we can. And we're going to put a 1, -1, and hold that constant spot with 0. What goes out in front? -1. And we bring down our 1, -1 times 1, -1 and -1. And then we don't care about this, right? We don't care about the remainder whatsoever, so don't even bother to take the time. Okay? What is our equation of that line then, that slant asymptote? X minus 2 is equal to our y. Okay? So let's sketch the graph of that. Well, that's nothing more than y equals mx plus b, where b is -2 and our slope is a +1. So we start down here at -2, x is 0, y is -2, and I have a positive slope, so I'm rising 1, running 1, rising 1, running 1, falling 1, going left 1, and so forth. And so we try to sketch that line as well as we can without a nice ruler as a guide. So we already know, actually don't. We're going to find out what our y-intercept is, right? So we plug in 0 for x. So 0 minus 0 over 0 plus 1. Going to get a 0, right? 0 in the numerator is okay, just not in the denominator. So 0, 0 happens to be both our x and our y-intercept, doesn't it? Okay. If it didn't turn out that way, you just say, I'm going to let y be 0. And what will happen if I do x squared minus x over x plus 1, and I cross multiply? Right? And we just factored that earlier to be x times x minus 1. So what makes y 0? Or what values of x are going to give us that intercept? Positive 1 or 0. So we'll also have a 0 at positive 1. When x is positive 1, y is also 0. Good question. So it looks like it's going to have to approach those two asymptotes, right? So it must do some sort of a turn in here. We don't know for sure, but 2 points is probably enough for us to get a reasonable facsimile of what this is going to look like. It'll do some sort of turn. We don't know how deep that turn is, and that's okay. If you want to put in a half, you could, and that would be okay. But we're not looking for perfection here. We're becoming human graphing calculators, but there's a limit to the time that we have, right? All right, so then we're going to say, okay, what's another number to try? Negative 2. So we're going to plug in negative 2 because it can't be negative 1. So negative 2 squared minus negative 2 over negative 2 plus 1. So negative 2 squared is 4, minus a negative is going to be plus 2, and negative 2 plus 1. So 4 plus 2 is, we'll have a negative 6. So at negative 2, we're going to be down here at negative 6. What's another number to try? Negative 3. All right, so negative 3 is going in. We'll have a negative 3 squared minus a negative 3 over negative 3 plus 1. So a positive 9 minus a negative is plus, right? And negative 3 plus 1, negative 2. So 9 plus 3. So at negative 3, we're at negative 6 as well. So it's doing some sort of like that. Questions on this one? All right, so didn't ask us for a range, right? We don't know for sure how far these are going up and down, do we? So on these slants, we're not likely to ask you for a range unless we ask you to graph it on the calculator. Does that make sense? We don't know where that turning point is. All right, so assignment, bold and underline required.